Okay, guys, good morning. So let's start our class. Before starting, just a reminder that you have the assignment tonight as the deadline for the submission. Okay, so the assignment is just 5 questions, and each will be like, say, so overall the assignment will be graded out of 10. And those are just 5 questions. So whatever we have studied, it is based on that. Okay, so please, this is the reminder. And so anything else you want to ask before we start the class?
Yes, sir, the next quiz will be
Okay.
on the
Yeah, next quiz, according to our tentative schedule, if I'm not mistaken, it is it is 21 to 25. So it will be next week. Okay. So on Thursday, yeah, on Thursday, I will give you the information about the syllabus and other things. Any other questions? Okay, so let's start. So in the last class, let's just quickly review the last 2 classes. So in the last 2 classes, we looked at conductors. We looked at what happens to a conductor when it is isolated, and then what happens to the conductor when it is connected to a electromotive force, that is a voltage source. And we have looked at the Ohm's law in point form, which is J is equal to J bar is equal to sigma E bar. So this is our Ohm's law. We have seen this, and then we have applied this to a small circuit from which we derive the Ohm's law, which is V is equal to IR, right? And then we also looked at the continuity equation, the current continuity equation, and then we looked at the boundary conditions, which are very, very important in electromagnetics. We looked at the 2 boundary conditions, and the 2 boundary conditions were these ones. First is the tangential component of the electric field across the boundary is the same, so they don't experience any change. So that's why we say it as continuous. And the normal component of the electric flux density, they follows this expression. Okay, and in the vector forms, they are this one. And then we also looked at what happens when you have a conductor as another medium. We have seen that since in the conductor there is no electric field, substituting that, we got the following information. What is that? We got the information that if you have any dielectric, then the dielectric can have, different field components. But as the dielectric comes close to the boundary, the tangential component must vanish in order to satisfy the boundary condition. And therefore, you only will have the normal component, and the tangential component will be gone near the boundary. And then we took 2 examples. We took this very nice example where we looked at how to find the electric field of other components, and then, the electric field in the other medium when one medium is given to us. We also found how to get the angle, right? And if you remember, this angles is very similar to what we did here, because here, if you see, if this is my boundary, just to share with you, because yes, in the last class we were a little bit faster, but if you remember, in a boundary, if you have electric field vector in any direction like this, then this will be the tangential component, and this will be the normal it should go the other way around. This is the normal component. And what is the angle? Angle, it always, as I told you, the angle is always defined as the angle your vector way makes with the normal to that boundary. So this is the normal, this is the normal. So this will be the angle theta. Now, if you see, if I say this as E tangential and if I say this as E normal, and if I can find its length, I can find its length. See, I got the tangential and I can find its magnitude, which is its length. Then the normal, I found its magnitude, which is its length. And what will be the angle here? Yes, tan theta is equal to opposite by adjacent. So which is nothing but the tangential component length over the normal component length, which is opposite by adjacent. And this is how I got this angle is tan inverse E2 tangential over E2 normal. And once we got both of these, we can find the angle. And then we also found the energy density in both the regions because we know the electric field in both the regions. We can find the energy density in both the regions. So this was like in the previous class. Now, before starting our next part, let's take some poll questions. Okay, so let's take some poll questions. Very simple. Be ready, guys. So the first question is the true or false question. So I will give you only 30 seconds and I will start counting at the end. So here comes the question. Yes. So please read it carefully and then answer it. So 10 seconds gone. $20 seconds gone. 24, 25. Please select 26, 27, 28, 29, and 30. Okay. So what was the question? The question says that the electrostatic boundary conditions state that the tangential components of the field vectors are continuous across a boundary separating two mediums. Is it true or false? So we have equal number of students. Yes, Mr. Abdul Al-Shahri, what do you say? Yes, Mr. Abdul Al-Shahri, what do you say?
Yes, I see it's true.
It's true. Yes, it's true because this is the first boundary condition. And it says that the tangential component will not experience any boundary. So the values will be the same. That's why it is E tangent ET1 is equal to ET2. This is what is stated here. Okay. So let's take one more question and then stop it. This question. Okay, so here, so 40 seconds for this question because this question is wrong. Sorry, not 40 seconds. I will give 1 minute. It's long. 45 seconds left. $30 seconds left. $20 seconds. $10 seconds. 56, 57, 58, 59, and 1 minute. Okay, so let me share the results. So what it says that if a conductor is connected to a voltage source, which of the following is correct? The static equilibrium is lost or the static equilibrium is not lost. First let's think about this. Mr. Abdul Rahim Al Mushrif, can you tell me? So will the static equilibrium lost or not lost?
It's not lost.
No, the static equilibrium is lost. Because see, the static equilibrium will not be lost when a conductor is isolated. That means if nothing is connected to the conductor, then the static equilibrium is not lost, and that's the static equilibrium is not lost, yes, and that's why inside the conductor the electric field cannot exist, because you have the equal number of positive and negative charges, and because of that your applied electric field and the electric field created by those charges inside the conductor, they cancel each other, and that's why there is no electric field inside the conductor. So this is all is valid when the conductor is isolated. Okay, when it is isolated. So we say that the static equilibrium, this is called as when the conductor is in equilibrium, the static equilibrium. So when you connect a voltage source, halas, the static equilibrium is lost because your number of charges are not different because of this external electromotive force. Your now charges are no longer equal. So that's why the equilibrium is lost, and therefore your conductor will now have an electric field inside it. This is when I explained the Ohm's law. So I hope you understood. Yes, Mr. Mushrif?
Yes.
Okay. So therefore, your answer is the, which one is the answer?
First one.
The static equilibrium is lost and the electric field exists inside the conductor, the first one. Okay. So guys, again, the main objective of, having this poll questions is, so that you can all, just keep reviewing what we have studied. Okay. So this course requires you to, review and do practice as much as you can. And every class we have new topics. And for the new topics to understand, we require what we have studied in our previous topics. Okay. So any questions before moving? Okay. So now today we are going to take lecture 9. And in lecture 9, we are going to now study capacitance. So we are going to study capacitance. Now, we have already studied about the isolated conductor and its properties. We have already seen that inside the conductor, just now I have repeated everything. And what are these? These are all your electric fields. I'm sorry, guys, the drawing is not that good, but we know that according to the boundary condition, the electric field must be 90 degrees to this conductor. Okay, so this is 90 degrees, this is 90 degrees, this is 90 degrees, this is making an angle, but I'm sorry for the drawing, it should be 90 degrees. Okay, so this should all be 90 degrees. So this is what we have studied about the conductor, and we have also studied about an equipotential body. So for an equipotential body, we know that the potential, wherever you go on that body or on that surface, equipotential surface, wherever you go, your potential will be the same, right? The potential will be the same. And if the potential is the same, then that is called as the equipotential body or equipotential surface. So now in our conductor also, it's the same. So conductor is also called as an equipotential body. Why? Because for the conductor, if you see wherever you go, if you try to find the voltage here, potential here, or a potential here or potential here, it will be the same wherever you go. The reason is, you can think it in this way. See, the potential difference. If you want to find the potential difference between this point and this point on the conductor, then you can do it. You have the expression minus integral over L E bar dot dl bar. So I'm saying that this is my A point and this is my B point. But since we know that it's an isolated, there is no electric field. So in this case, VA becomes VB. So the potential becomes same everywhere. Okay, so this is again not new. What we have studied, we are just applying to the conductor. Now, what we are doing in our class now, today we are studying about capacitance and the capacitors. So therefore, now we are now bringing these two conductors, not one. So now we have two conductors. So we are bringing these two conductors close to each other. Okay, they are isolated again. See, they are isolated. They are not connected. So this is some dielectric medium, and this dielectric medium can be air or it can be any dielectric material. Now I am giving a potential difference, or I'm keeping these two conductors at a potential difference. That is one conductor and the other conductors. Now what is happening is we are say with the help of our external voltage source, we are making one conductor positively charged and another conductor negatively charged. And we are doing in such a way that the charges here and the charges here are equal in magnitude. So here, if it is positively charged, then here it is negatively charged, but their magnitudes are the same. Now, in this case, what will happen? So in this case, a capacitor will be created. And the capacitance of these two conductors, is given by C is equal to Q over V. Q is the magnitude of the charges and V is the potential difference at which you have kept these two conductors. And now from our electromagnetics, if we write the expressions, we will see that the charge Q, we can write the charge Q in terms of, can anybody tell me what is this? Yes, maybe Mr. Ahmad Al-Ghamdi, can you tell me what is this expression? This is which law?
This is for the surface.
Yeah, this is a law that we have studied. Charge is nothing but closed surface integral d bar dot ds bar. D bar, I'm just writing D bar as epsilon E bar. So which law is this? Do you remember? Maybe Ali Al-Shams, can you tell me?
Yes, doctor.
Yeah, which law is this?
The surface charge.
Yeah, yes, I know. It's a surface charge. But there is a law given. This is a law. Okay, it's a law. And we have studied that law. Yes, Zuhair, you raised the hand first.
It's the Gauss law.
Exactly. This is the Gauss's law. Yes, both of you are correct that it's a surface charge, but that is put under the umbrella of a law. And that law is the Gauss's law. Yes, Hassan.
I just want to lower my hand. I don't have a question.
Okay, thank you. So I'm now writing. I hope both of you understood, right? Mr. Ali Al-Shams and Ahmad Al-Ghamdi.
Yes, doctor, I just said Gauss's law. So
Okay.
I was correct, right?
Okay. Yeah. You said, see, it's a surface.
Yeah.
It's a Gauss's law. Okay. So I'm replacing Q with this, and I'm replacing the potential difference with our definition, which is minus integral over L E bar dot dl. So this is the general expression of finding the capacitance of any type of two conductor capacitor. So that's why I'm putting it as a generalized one. They can take any shape. And now, what is this electric field? From where I'm getting this electric field? Because if you are keeping these two conductors charged now with positive charge here, negative charge here, then automatically an electric field will be created, because a force will be created between these two based on how much is the distance between them. And from the force, the electric field will be created. And this electric field will be in this region, the region which is separating these two conductors. This is the electric field. And the charge and the potential difference, this E that you are seeing, is this electric field. Okay. And now what is this potential difference V? Here I'm explicitly showing the potential difference V is, if I say that this is at a potential V plus and this is at a potential of V minus. Okay. And I'm saying this as 1. And if I'm saying this as 2, then the potential difference is V plus minus of V minus. This we have seen is minus integral lower potential to higher potential. So lower potential is the negative. So it is 2 to higher potential 1 E bar dot dl. So dl can be the length. So you can select any length between these two. So that is the potential difference. And the charge is nothing but the charge of this one, which I'm assuming it as Q. So this will be plus Q and this will be minus Q. But its magnitude is Q, is integral d bar dot ds bar, and it is closed surface integral of 1. Closed surface integral of 1, this one. You can also have it for this one. It will be the same. Okay, so this is the total charge on the positive conductor. Now, since our charge is non-zero and our potential is non-zero, because if our potential becomes 0, then the potential difference becomes 0, the charge becomes 0, and these two becomes isolated conductors. But now when I give the potential difference, then you will have charge here, you will have charge here, and they will be at a fixed difference, and that creates a capacitance. And now our objective is to find that capacitance. Now, how do we find that capacitance? There are two methods. Okay, so the book has shown two methods, and I'm just summarizing those two methods here. So what are the two methods? When we know the charge on a capacitor, then we can use the first method. Or when we know the potential difference at which the capacitors are kept, then we can use the second method. So in the first method, assuming Q is given to us. So assuming Q is given to us, we will first determine the potential difference in terms of Q, and therefore this we will use Gauss's law. This is our first method. Second method, when a potential difference is given to us, then we will determine the charge on any one conductor in terms of the potential difference, and this involves solving Laplace equation. So this is our next step. So in today's class, we are going to look at number 1. Okay, that means when we know the charge on our conductor. And what are the steps? The steps is, for the first method, first looking at the shape of the conductor, you decide the coordinate system. Second, we assume that we know the charges. So we will put the plus and minus Q charges on my conductors. And then we will find the electric field between the two conductors. And from there, we will find the potential difference in terms of the electric field. And then we can find the capacitance. So let's take the example. Our example, first example is the most simplest one, which is our parallel plate capacitor. And our objective is to find the capacitance of this parallel plate. Now, if you see here, this is my top plate, which is kept at a charge plus Q. Bottom plate kept as a charge of minus Q. So this is known to us. And D is the distance separating these two capacitors. And the surface area of this sheet, this plate, is S. Surface area, I hope you got the point, right? So because in the 3D plane, it will be like this. Right? So this will be your D. So S is this surface area. This is my S, the surface area. Okay, and this is at a charge of Q plus, and this is at a charge with Q minus. Now, what is these arrows? These arrows are giving you the indication of how the electric field will be. So if you guys remember, let's apply our knowledge that we got for an infinite sheet. Yes, for an infinite sheet, in the infinite sheet, we got it. We found how the electric field will be when you have two charged plates, right? Then you remember? So the field will only exist between the two plates, and it will be pointing away from Q and away from positively charged plate and towards the negatively charged plates. Remember, we did this example. So there will not be any field existing here. There will not be field existing here. This is when these plates are infinite plates. That means they are infinitely long. So you don't see the edges. That's why it will be perfectly, they will be normal to the surface of this plates. But we know it very well that, it cannot exist, in practical cases, you cannot have an infinite sheet. So therefore, what happens is the expressions that we got for our plates, the expression, what was this expression? Do you remember? It is rho S over, yes? Anybody remember?
2 epsilon.
Epsilon.
Yeah, rho S over epsilon. Rho S over epsilon. This was what we got for the plates, upper plate and lower plate, rho S over epsilon. So this is only valid for infinite plate. But we are going to use this expression in our problem, assuming that these plates are infinite. But just to give you an idea, when the plate is no longer infinite, then in that case, what happens is, as you go to the corners, then your field will no longer be this value. It will no longer be straight. It will start curling like this. That means you will now have, it is made up of two components. See, you will see like this. So this is for the finite plate. You will see something like this. These are called as field fringes. And this will appear when we go towards the edges. And at that place, this expression is no longer valid. So maybe when you are at the center of the plate, the expression is valid because you don't see the corners. That's why. However, in our problem, we are assuming that our sheets are infinite. So we are just neglecting this. We are neglecting this field fringes. And that's why we are using this expression. Okay? Done? And what will be the expression for the electric field for these fringes? It will take, So you have to go to the Coulomb's law, and you have to apply Coulomb's law, and then you need to find those expressions. So it will not be so straightforward. It will be a little bit complicated. Done? Okay. So now let's come back to our problem. So now first we need to choose the coordinate system. So which coordinate system would be the best for our parallel plate capacitor? We know it, that because those are parallel plates, the best suitable coordinate system is our rectangular coordinate system or the Cartesian coordinate system. So that's why I assumed that this is my x-axis. Okay, this is my x-axis. And these are my plates, which is in the YZ plane. Next, we have already assumed the charges plus Q and minus Q, and because of this, the electric field has formed. Now, let's find the electric field. We know it very well. We have just now seen it. So your electric field will have only one component, right? It will have only one component because it will be only parallel to my x-axis, because I'm neglecting these fringes. And I'm also assuming that the material between these two conductors, so this is filled with a dielectric material, and this dielectric material has a permittivity of epsilon. So epsilon is the permittivity of this material. I'm not assuming it as a free space, any material. Then the electric field, so now I'm working with magnitudes. So because E is, we know that it is only x component AX, but I'm now working with magnitudes. So therefore, the magnitude of the electric field for the upper plate and as well as for the lower plate, it will be the same. Yes, Ali?
For electric field, isn't rho S over 2 epsilon for the infinite plane?
Say it again, Ali, please.
For infinite plane, isn't rho S over 2 epsilon? Not
That is for, yeah, that is for a single plate. But here we have two plates. So it will be rho S over epsilon plus rho S over epsilons. So it will be rho S over 2 epsilon plus rho S over 2 epsilon. So it will be rho S over epsilon.
Okay, I get it.
Okay, so because of these two plates, this electric field will be rho S over epsilon. So if you are near this plate, which is this one, the electric field on the upper plate, if you are near to this one, so here also it will be the same value, rho S over epsilon. And for the lower plate, which you are near here also the electric field will be the same, which is rho S over epsilon. And now I'm writing rho S, which is the surface charge of this plate, surface charge density of this plate. I'm writing in terms of the charge. So can I write it in terms of the charge Q as rho S is equal to Q over S, because my surface charge density is uniform. So therefore, I do not need to go and use the integral. I do not need to go and find Q as integral of rho S ds, right? Because I know that this is uniform. This is uniform. So I can easily take it out. So it will be rho S of integral over S ds. And what is the integral? What is the surface area? What is the area of this sheet? We have already assumed that the area of this sheet is S. So Q is nothing but rho S multiplied by S, or rho S is what? Q over S. Okay. So that's why I'm just substituting Q over S here. Now, once I got the magnitude from our previous experience on the infinite sheets, and now can I write, so therefore I was working with my magnitude, but now can I write in vector form? Yes, my electric field is Ex times Ax. So electric field will be the magnitude, which is Qs over epsilon, times which Ax? So is it a positive Ax or a negative Ax? Can you tell me, guys?
Negative.
X or negative X. See, this is my assumption that my direction of X direction is this, but my field is in the opposite direction, right? So that's why the unit vector is negative, and this minus is coming from that unit vector. Okay. And by the way, I think when we were dealing with the sheets, a couple of questions raised by the students when I told that it's always better to work with magnitudes and then let the unit vector decide the sign. And I have checked, this will be valid for any type of problems. Okay, any type of problem, not just restricted to sheets. You can use it for anything. So for example, here we are using it. See, we are working with the magnitude. We got the magnitude and we are allowing the unit vector to decide the sign. How? By going and analyzing it. When we analyze, the electric field is in this direction and therefore it is minus AX. So this is the electric field of this problem. Now, once I got the electric field, then I want to find the potential difference. And the potential difference is minus integral. Lower potential is 2 to upper potential is 1. So this is my 2 lower potential. This is my upper potential 1. Then the potential difference will be minus integral 2 to 1 E bar dot DL bar is equal to minus integral 2 to 1 E bar dot DL, because our electric field has only one component. So therefore this will reduce to only EX. And what will be my DL here? What will be my DL here? DL will only have X.
dx.
Only DX. Okay, DX. I hope this is clear. This will be very straightforward because your electric field E will be EX AX plus EY AY plus EZ AZ. And DL general expression is what? DX AX plus DY AY for our Cartesian coordinates plus DZ AZ. Now, since only we have this component, so only when you do the dot product, only these two will exist and you will get EX multiplied by DX, which is this. And we don't have this, we don't have this, they will all go to 0. They will all go to 0. So you will have only EX dx. So that's why you have EX dx. Okay, now I'm substituting the magnitude. So which is minus Q over S over epsilon, which is this one. I'm sorry, not the magnitude, the EX value, the EX component value, which is minus Q over S over epsilon. Dx is as it is. And now, since these are all constants, I can take it outside. So it is integral 2 to 1 dx. And what will be the integral 2 to 1 dx? The integral 2 to 1 dx is nothing but the distance that you kept between your lower plate and your upper plate, which is your d value, right? Because you are integrating from here to here, here to here. So dx from here to here, which is nothing but the distance value, which is your d. So therefore, your potential difference is Q over S over epsilon times d, or what is Q over S over epsilon is nothing but, I'm now writing in terms of, I'm saying that now this is nothing but, this is my magnitude E, right? So I'm now writing this in terms of the electric field magnitude. So the potential difference is electric field magnitude E times d, or Qs over epsilon times d. Once we got the potential, the last step is that you find the capacitance, and the capacitance is Q over V. So Q over V. What is V? V is Q over S over epsilon times d. Substitute here, Q and Q will cancel, and you will get as epsilon s over d. This is the capacitance. And this is what we have been using as an expression for a parallel plate capacitor. Okay, got it? So therefore, how was the method? The method was that we know Q. From Q, you find the electric field. From there, find the potential difference. And then from there, find the capacitance. Okay. Now, what will be the energy stored in a capacitor? Again, the energy stored in a capacitor is equal to half CV square or half QV or Q square over 2C. This we have been using these expressions for the energy stored in a capacitor. Now, can we derive here? Yes, let's derive. So what it is saying, we already know that this is my electric. So I'm taking the same example as the previous one, this one. So if you see here, it's the same example. This is positively charged plus Q, negatively charged minus Q, surface area S, placed at x is equal to 0, and this is x is equal to d, so that the distance between them is d. So therefore, the electric field for this one we already derived is minus Qs over epsilon times Ax, right? So let's find the energy density first. So what is the energy density? Small we is half epsilon E square. So it is half epsilon. So magnitude of this will be, what will be the magnitude of this? The magnitude of this will be Qs over, it will be Q over S over epsilon square, which is Q square over epsilon square S square. So this is my energy density. Now, therefore, how can I find the energy? WE is if I get the energy density and integrate it over the volume. Integrate it over the volume. Now, what will be the volume here? Now, before that, if you see the energy density expressions, they are all constants, right? They are all constants. Q is a constant, S is a constant, epsilon is a constant, everything is a constant. So therefore, in our case, I can take WE outside. So it will be WE integral over V d. Now, what will be the integral over the volume? Where is my volume here? My electric field is between these two plates, right? So my volume is this volume. How can I find the volume of this? This is nothing but it's a cuboid. Cuboid, right? It is nothing but it's a cuboid. It's something like this. Like this. Now I want to find this volume. So it is the length multiplied by breadth multiplied by height. But we don't know length and breadth, but we know its value. Length multiplied by breadth is nothing but the surface area. So this surface area multiplied by this height d will give me the volume which is between these two plates where our electric field exists. And that will be the volume. And that is given by S multiplied by D. S multiplied by D. So here, if you see, it is S multiplied by D. Now, when you simplify this, you will see that the energy stored in a capacitor, you are getting it as half CV square, which is the same as this one that we are using in our previous courses. And in fact, what you will see is this is not just for valid for this parallel plate capacitor. This is valid for any shape capacitor. Any shape capacitor, these expressions are valid. Okay. Now, this is another example. Derive an expression for the partially filled capacitor. Okay, so we will take this example. Partially filled. Now, what do you mean by partially filled capacitor? If you see here, this is the positive charge. This is the negative charge. This is placed at x is equal to 0. This is placed at x is equal to d because the distance is d. Now, the material between these two parallel plate Capacitor is not a single material. It's two materials, unlike our previous example. So if you see this material, this much of height D1 is dielectric material of permittivity epsilon 1, whereas this part is free space, air. So therefore its permittivity is epsilon 0. And since this is D1, then this distance is D0, which is nothing but the overall distance D minus D1. Now, for this case, how are we going to proceed? In a very similar way. First, decide the coordinate system, again the Cartesian coordinate system, assume the charges, which we have already done. Now our objective is to find electric field. So in this case, how would be the electric field? So because now we have two materials and there is a boundary, so will the electric field here and will the electric field here, will they both be the same? Yes, will the electric field here and electric field here will be the same? Yes, Mr. Nawaf, can you tell me? Will they be the same?
I think yes.
No, they will not be the same because they are in different materials, Nawaf. See, this is air, this is dielectric, right? So,
Yes.
yeah, so in air, the electric field will be different. In the dielectric, the electric field will be different. Why? Because of the boundary conditions.
Yes. Yes.
Because, so therefore, in our previous case, we just found only one electric field value. But here, our electric field value will change when we do the integration here, and it will change when we do the integration here. Because here the electric field will be different, and here the electric field will be different. So that's why if you see, now I'm defining electric field E as E0 0 bar when I'm in this region. That is when I'm from D1 to D. So when I'm between this, because this is D1 and this whole is D. So when I'm between this region. And then it is E1 when I'm in this region. That is from 0 to D1. 0 to D1 is this one. Then D1 to D value, because this is the D value. This is my D value. And D1 to D is this one. Dielectric medium. Now we just find our E0 bar and E1 bar, and that's it. Now how to find E0 bar and E1 bar? Because they are not equal. Boundary conditions. See, now here we have only one component, which is this component, right? Because electric field is like this. Now what will be the value here and what will be the value here? We need to find. Now we know that this is the boundary, and we know that this is the electric field, E0 bar, which is like this. And here it is E1 bar. So it doesn't have so many components. It have only one component, which is your X component, because this is the X direction. Now, boundary conditions. What does the boundary conditions tell about E0 and E1? Because we only have normal component, so therefore we don't apply the first boundary condition, we apply the second boundary condition. What is the secondary boundary condition? D1 normal is equal to D2 normal. And because both are dielectrics, there is no surface charge. That's why D1 normal is equal to D2 normal. So what is D1 normal? Normal epsilon 0 E0, right? Can I say E0? Why? Because we have only one component, because E0 is made up of only one component, which is the normal component. So therefore it is epsilon 0 E0 is equal to epsilon 1 E1. Got it? And if I say it in terms of vector, so D1 bar is equal to D2 bar, or epsilon E1 bar, 0 and 1. So epsilon E0 bar is epsilon E1 bar, and therefore your E0 is, we have just now got it for free space. it is Q over epsilon 0. But my E1 will be Q over S over epsilon 1 in this region, epsilon 1. And then if you check, they both satisfy this boundary condition, which will be epsilon 0 E0 is epsilon 1. They will both satisfy this. So this is important. They need to satisfy. Otherwise, these expressions will be wrong. Halas, we got E0 and E1. So therefore, our electric fields will be in terms of vector, because this is my AX direction and this is my my field direction. So it will be minus and minus. And therefore, my potential difference will now be evaluated for 0 to D1 and then D1 to D. For 0 to D1, it is E1, and 0 to D1 is E1 D1, and D1 to D is nothing but E0 D0. So this is my potential difference, and therefore my capacitance will be C is equal to Q over V, which is this one. Okay, so I think we will stop here, and in the next class we will continue. So I will take the questions about this in the next class, because we don't have time. Okay, guys? So thank you very much.
Thank you.